Okay.
All right. Thank you so much. First of all, thanks to the organizers to put up such a brilliant meeting and for having me as part of it. I'm flattered. Yeah, I would like to talk about neutrinos from supernova from a more or less critical point of view. At least this is how I see it. And I will start with the summary. This is the neutrino signal, how we believe it may look like from a canonical core collapse supernova, starting from the luminosities shown in the top panel and the average energies at the bottom panel. This is within the supernova domain. Sure. Try. Am I logged in?
Yeah, that's I think it's wrong link.
It's the wrong link.
Yeah, this is the number.
Okay.
Yeah.
I took it from the email you sent.
Yeah, and there was like, I made a typo.
There's a typo. Doesn't work. Going. Meeting ID 304 304 150 5224. Unable to join the meeting.
5254. It's like again.
54. Oh. Okay. Apologize for the delay. Where's Zoom? Here. Time. Okay. Good. So, how do I turn off these people on the right-hand side?
You can just leave.
Anyway, they'll stay. You have to live with them. Can't see my mouse.
A bit more.
I know, but I can't see my mouse on the screen. Anyway, forget about it. Let's move on. We don't have time for this, I guess. All right. So I would like to walk you through in my presentation how this neutrino signal comes about from the core bounds, the sudden rise of the electron neutrinos, accompanied with the appearance of all other neutrino flavors, followed by a post-bounce mass accretion with fairly high neutrino energies, and then followed by a deleptonization that lasts for several, presumably tens of seconds, in which the fluxes, neutrino fluxes, decrease exponentially. We've had a great talk yesterday by John Beacom, who had explained us how neutrino detection would give rise to thousands to tens of thousands of neutrino events. In the current and future detectors, this is a sample of reactions up, which you can't see much. Dominant reaction channel is the charge current, anti-neutrino absorption of protons bound in the water molecules. And we have done detector analyses for a supercamucanda and a fictive argon detector, where there's additional reaction channels. And we basically confirmed the statement, yesterday's statement, that we'll have thousands up to tens of thousands of neutrino events for a fiducial galactic supernova. With the continuous decrease on of the signal for several seconds, perhaps even tens of seconds, until we reach the sensitivity threshold for the detectors. Unless there is something extraordinary happen, that's shown in this figure, namely a phase transition. If a QCD phase transition happens from normal nuclear matter inside your hot protoneutron star to some exotic phases of matter, then instead of having a continuous decrease following the post-bounce mass accretion phase, you'll have a sudden rise in the neutrino luminosities of all flavors, as well as the average energies rise, and only after that the explosion would set in, exponentially decrease. And this is a talk that, the topic of the talk will be mostly covered by Andrea tomorrow. She will talk a lot about that. But I couldn't help myself to put the Supernova 9087A neutrino data, at least the early neutrino data, in. I quenched it a little bit. I reduced the time window from the first set of data points to the second. The third, which are at 7 seconds, are obviously not in because the simulation didn't run that far. And that is an interesting idea that one might or might not follow more closely to be able to explain the very high neutrino energies that come at around 1.5, 1.7 seconds. Now, because they're quenched, they come at 1 second in order to constrain perhaps things like the onset density for quark matter. I also couldn't help myself, after yesterday's very interesting discussion between John and Thomas, to look at our models. And I felt a little bit obliged because John Beacom also was looking at agile Boltzmann runs, and we had the honor to continue working on the agile Boltzmann code for many years now. So I felt obliged to also look at some of our models, and this is shown here. So I plot a 25 solar mass exploding model where we artificially enhance the explosion onset after about, I don't know, what is that, 0.7 seconds or so due to neutrino interaction enhancements. And in comparison to a failed supernova of 40 solar mass, which is the red lines. And at the bottom right panel, you see the average neutrino energies for antineutrinos. And I plot the Supernova 9087A data here, now not quenched. And in fact, I do not see much of a problem in neither explaining the early neutrino observations of at least super Kamiokande and the late neutrino observations, which are due to the deleptonization of the neutrino burst. Since this workshop is a lot of symposium, is a lot about gravitational waves and detection, the idea that I have figured during the last couple of days is basically to identify common features in the gravitational wave signal, which will allow us to relate to unknown quantities like the surface gravity, or in this case, the average density, if this is the dominant mode. So I think it would be good to be able to figure out either one of those two from another source, and I think neutrinos do provide this, this possibility if one assumes that the binding energy that is released in a supernova explosion is basically proportional, if not identical, to the neutrino energy that is received or detected at a neutrino detector for a long period of time. And for that, I've done a little analysis here. So I plot basically the energy that is emitted in neutrinos for a certain period of time from 3 different supernova simulations launched from a 9.6 solar mass progenitor. I can't show it. This is the red line, the black curve, from a 18 solar mass progenitor and from a 25 solar mass progenitors, all of which are exploded. The 9.6 explodes naturally in spherical symmetry. The other ones are enhanced. And consequently, you get different neutrino emission pattern. This is the total neutrino energy emitted as a function of time. And in comparison to the actual mass and radius of the neutron star, which is the solid lines. And at late times, those quantities basically coincide. At late times, those quantities basically coincide to give the masses of these 3 objects, a low mass, an intermediate mass, and a more massive proton or neutron star. But at early times, this agreement is fairly terrible, and the reason for that is that the proto-neutron stars are still hot. The 25 solar mass features peak temperatures of almost 50 MeV for a very long time. So only if we're able to detect neutrinos until very late times, I think this comparison at the high precision is meaningful. Also in particular because the uncertainty in the radius is actually fairly small. It's only on the order of a few kilometers for those hot neutron stars. But I think this is an interesting prospect. Neutrinos are produced in the context of quark-collapse supernova from various weak interactions. John had talked about this already fairly extensively. So reactions on heavy nuclei play a role mostly during the infall phase, during the collapse phase, dominated electron neutrinos. At bounds, we have then also the co-production of antineutrinos and mu and tau, heavy lepton flavor neutrinos, mostly from pair processes down here. Neutrinos also scatter elastically on nucleons and nuclei. Oui, magic. And post bounds, we also have electron captures on protons and positron captures on neutrons when matter features high enough temperatures. And that gives rise, at least during the early phase, to a clear hierarchy in the average energies, depicting the decoupling strength, and then the neutrino fluxes come also in a certain hierarchy where the differences between electron antineutrino and electron neutrinos, also the flux difference, basically reflects to some extent the nuclear physics involved in these processes, which I'd like to talk about later. Some time ago, we looked at an additional channel. So if people think now the whole picture is understood of neutrino emission, even during core collapses, is not the case. Because, for example, nuclei might exist in excited states who de-excite not only due to the emission of photons, but also due to the emission of neutrino pairs of all flavors, in fact. And we followed an old idea from George Fuller and Brett Meyer in the 90s, who had constructed some double peak structure of the excitation strength of nuclei in dense and hot matter. This first peak is basically Gamow-Teller, the second is the first forbidden. Thanks to the help of Karl-Heinz and Gabriel in the GSI, we also came up with a double Gauss structure, folded the excitation strength spectra of the nuclei with the de-excitation strength, so folding it with the Boltzmann factor, and then computing the emission neutrino spectra for pair neutrinos. We implemented those two strength functions in the supernova simulations, and what we find is that the neutrino fluxes, this is the neutrino luminosities, without this process are basically enhanced by 3 or 4 orders of magnitude for most of the time of the stellar core collapse. We were hoping to get a larger enhancement because temperatures are very high, but they reach only a comparable magnitude when other weak processes start to populate these states as well. And at that time, the heavy nuclei basically disappear, they're dissociated. So this is the phase when you have the transition from inhomogeneous nuclear matter with neutrons, protons, and nuclei to a phase where there's mostly neutrons and protons present. That was an interesting project. Neutrino energies of these neutrinos basically suppress. Bear in mind that the blue curves here are without this reaction channel. So the only source of mu and tau neutrinos during collapse phase is basically electron-positron annihilation, and therefore the fluxes are so low and the average energies are a little higher. A word of caution, when you're dealing with a neutrino signal and you want to make predictions for that, and a good neutrino transport scheme is essential. Agile Boltzmann implements Boltzmann neutrino transport. This phase space is discretized in cosine of the scattering angle, and behind this person here is the energy. So the neutrino distributions are treated angle and energy dependent, and we treat all the 6 species individually. This has then consequences for the neutrino decoupling. So the region where neutrinos decoupled are shown here as a function of different energies for a density profile and a temperature profile, typical post-bound situation. The bottom panel shows the abundances that are there, so protons, neutrons, helium, but also light clusters. And if on top of that, I am plotting the corresponding neutrino decoupling regions, then inside the neutrino sphere of lowest energy, 0.5 MeV in this case, neutrinos are completely trapped, outside of which neutrinos are completely free stream with the highest neutrino energy bin, and in between they couple, and thereby they establish a cooling layer at higher densities and a heating layer at lower densities. And this phenomenon is actually the reason why neutrinos do not canonically explode in spherical symmetry, because the cooling rates, this is the energy deposition as a function of density in one of the simulations, is substantially larger than the neutrino heating contributions. The same is true for all the other reaction channels. So multi-dimensional simulations are essential to explain the supernova paradigm, I believe. This is nevertheless interesting to look at the lowest mass, stellar mass bins. This is the interstellar mass function for 2 different slopes mimicking metallicity dependence. So that would be solar metallicity, that would be subsolar metallicity, where basically 20% or 25% of all massive stars sit in the first 2 bins between 8 to 10 solar masses. So we took a closer look at these stars. There's a lot in the literature about these intermediate mass stars, yeah, between 8 to 10 solar masses. Bernard has done simulations about this. So this is a 9.6 solar mass model here that has a very early explosion onset. It's the shock radius and the features fairly low explosion energies for the time of the simulations. He also looked at helium stars, which feature similar electron capture type supernova explosions. In Princeton, people have done simulations also. This is this 9.6 solar mass model, I believe, in 1D and in 3D. So also there, very early shock revival, short to almost no period of shock stalling. Thomas and Garching with a PhD student, and I think is published by now, have done similar simulations. This is the black curve is the canonical Nomodo 8.8 star. The blue curve is the blue curve is the Nomodo star. The black curve is the 9.60 metallicity model, and then there's a red curve is a 9 solar mass solar metallicity model. So all these stars belong to this class. And interestingly here, that despite the structure of the black and the red curve, the stellar structures are very similar. They feature very different explosion dynamics. So for the red model, so the solar metallicity 9 solar mass model, there's actually a period of shock retreat before neutrino heating pushes the shock away and triggers the explosion onset. So we took on that challenge to simulate those models as well. And what you see here is two simulations, one that features a low phase space resolution with only 2 angular bins and 24 energy bins, and the high resolution with 6 energy bins. And up to the moment post-bounce, both coincide, but the low resolution, the shock is revived significantly earlier than for the high resolution run. The explosion is more energetic, the shock velocities are larger, and the neutrino-driven wind is much more pronounced than in the high resolution run. That has consequences for, I don't have time, Jim. Sure I can. So until bounce and early post-bounce phase, both simulations coincide, sample at the same time, and then the shock revival takes place basically abruptly, similar to what we have seen in the literature for that zero metallicity 9.6 solar mass model, and it is later on followed by the other one as well due to neutrino heating. Shock evolution is shown here. It's a low resolution model. Those are the 2 high resolution models. So it also depends how you treat your neutrino, your electron captures. So the Euler-Galvis rates, this is the microscopic shell model calculations of Gabriel and Karl-Heinz from back then in 2010, give a much more compact core at bounce. Bernhard explained this on Monday briefly, but this is the case in comparison to the proximate treatment of Brun. So even that makes a difference in terms of shock revival. So I don't think the last word about that progenitor mass range has been said yet. Consequences about the wind, the YE in the wind. For the low resolution, we get the very early, slightly neutron-rich pocket, followed by a mostly neutron-rich neutrino-driven wind. In case of the high resolution run, there's little to no neutron richness. This is in agreement with the simulations done in Garching, analyzed by Alessandro Mirizzi in a paper where he shows the neutrino-driven wind for 2 different equations of state for exactly the same progenitor, and you see the wind is mostly proton-rich. That is a bit in contradiction with the paper by Shin Giavanaggio and others later, though, who have found that the Nomodo 8.8 and the zero metallicity 9.6 models have very similar nucleosynthesis pattern. Okay, so in this case, Thomas is right. Have a very broad distribution of YE that go very low YE. Okay, good. Thank you. I bring this up just to say that there is still some controversy in this progenitor mass range, and I find this very interesting. So how can we understand the weak rates? I always like to look at the neutrino opacities to explain this. For mu and tau neutrinos, for electron antineutrinos, and for electron neutrinos. And mu and tau neutrinos, the opacities are dominated by elastic scattering on nucleons. They have the largest opacity, followed by inelastic neutrino electron and positron scattering, and then the pair processes, they are relevant at higher densities. In addition to the electron antineutrinos, for the electron antineutrinos, in addition, we have the charge current contributions that are somewhat lower, and the reason for that is because matter is very neutron-rich at the neutrino decoupling sphere, and hence for the electron neutrinos, this is the dominant reaction channel. So if you look at these reactions that dominate for the energy exchange, we're not dealing with free neutrons and protons, but we're dealing with neutrons and protons that are strongly interacting, and most equations of state treat neutron and proton single particle properties through effective degrees of freedom. So they have an effective mass. The mass is less than the vacuum mass, and the potential energies are large, in particular because we're very neutron rich. That has consequences if you calculate the neutrino opacities. Depending on your favorite prescription of the neutrino opacities, the neutrinos basically have to overcome the energy difference between neutrons and protons. In one case, there's no threshold. In the other case, there is a threshold. So the antineutrinos have a threshold at low energies that is by no means relevant due to the rest mass difference, but relevant due to the potential differences, which can be large. In this case, is 8 MeV. And below that, there's no contributions. We have found not so long ago that this potential difference between neutrons and protons actually opens up a new opacity channel, it's the inverse neutron decay. That is then because of the different sign of the electron antineutrino has its largest contributions at low energies. Including this channel in the simulations actually gives mostly during the neutrino-driven wind phase, so for the protoneutron star deleptonization, quite a suppression of the average nu E bar energies and a slight feedback to the fluxes because your deleptonization timescale changes a little bit. So in fact, you make the difference between nu E and nu E bar energy smaller. And that has also consequences to the wind YE, at least in the 1D simulations. We see that without the neutron decay inverse channel as an opacity, we get slightly neutron-rich ejecta at later times. Well, let's say at early times. Equation of state is constrained to some extent from chiral perturbation theory up to some density. Interesting to note here, I plot here a variety of supernova equations of state that are commonly used in the community, is that the relevant density range is actually low densities. So of course there are large variations at high densities, but the low density variations are more relevant because that's where the neutrinos decouple. Even though the bulk properties of these equations of state are also different to some percent, there are large differences in the single particle properties. In particular, Latimer and Swesty underestimate these potential differences between the yellow lines, whereas other models like this FSU Gold and IU FSU, they overestimate the potential differences between neutrons and protons. And I think the best models that fit into this is the DD2 and maybe SFHO. I don't know, making too much of an advertisement here. At high densities, we also have some constraint and a lot of progress going on. Recently, there was a measurement of the pi plus, pi minus ratios in Riken in Japan, who have given us a value of the nuclear symmetry energy above nuclear saturation density. So those kind of experiments are very important and very helpful. So depending on your favorite weak interaction matrix element, with or without weak magnetism, with or without quenching of the coupling constants, and with or without pseudo-scalar contributions, the variation, this is 3 different equations of state, can be actually large. In particular, the cutoff, so the effective Q values for these reactions. And that all that has influences on the neutrino heating and cooling. Now coming to my summary, what we still need to do, I think there's a lot of potential in relation of equation of state and weak rates. So Kamil Sokolovsky, PhD student in Wrocław, is currently working on the nuclear equations of state that go beyond the mean field by the inclusion of Fock interactions. Fock terms do not only give rise to scalar self-energies, which modify the effective masses, and zero self-energies, which modify the chemical potentials, but also vector self-energies, which would modify the momentum. And you see that all these quantities have some momentum dependence, and in particular, the vector self-energy has strong momentum dependence in comparison to the canonical mean field values that are those lines here for the same nuclear interaction model. This also opens the potential channel to investigate pions. So for that, we do an RPA kind of calculation where you have a pion coming in, coming out, and the loop in between is basically what you have to calculate is the pion polarization loop, where we use the Hartree-Fock, relativistic Hartree-Fock dressed nucleon properties, and that is the prediction for the pion self-energy, pi minus, pi plus, and pi zero, where we find basically an enhancement of the pi minus masses, a suppression of the pi plus masses, and little to no effect, zero self-energy for the pi zero, in comparison to Sanjay Reddy's and Bryce Fall's virial large prediction, which strongly suppressed the reduction of the pion mass with increasing density, which in a recent calculation done by revisiting these results, also Sanjay and his team find actually an increase of the pion mass with increasing density. Now, if you make pions heavier, then you suppress their abundance with increasing density. This is what we basically confirm in comparison to the virial equation of state, where you make the pions lighter. So in which case you would increase the pions to very high values and would not only have to revisit your nuclear equation of state, because for charge neutrality, for every pi minus you basically produce a proton, and then for baryon number conservation, you have to have one neutron less. So this is the indirect impact of the inclusion of pions at high densities on the nuclear equation of state, but you will also run into problems of pion condensation. We had nice talks this week by several authors, so I don't need to talk about that. Muons, we've also looked at the muon interactions, and the longest simulation that we've run with muons in 1D are now 30 seconds, and unfortunately you can't see it, but even at 30 seconds, the muon chemical potential and the electron chemical potentials are not the same. So the condition of weak equilibrium between muonic and non-muonic reactions is still not fulfilled at 30 seconds. And that's the reason, because it's still fairly hot. The muon abundance generally stays low. A word of caution here, most equations of state have a sensitivity of the hadronic charge fraction that is on the order of 10 to minus 2. Light clusters, we've looked at the light clusters, neutrons, protons, but also deuteron, triton, and other hydrogen isotopes like hydrogen-4 might be abundant in the supernova. We also looked at hydrogen-5 and helium, other helium isotopes, so that was an interesting task. This relates to the question, however, how do we do the transition? How does the liquid-gas phase transition take place? And most canonical models simply assume a sudden drop of the abundances of all clusters at saturation density. Quantum statistical calculations of Gerd Röpke have actually shown that this is not the case. Heavy and light clusters actually drop already fairly below. This is saturation density. And we've put this in this improved prescription of the suppression of clusters into the supernova simulations. And we found very different conditions at the liquid gas phase transition, slightly before and at bounds. And the reason, so this is the temperature profile, for example, this is the electron fraction profile. This is the time when the stagnation front forms shortly before shock formation. And the reason is simply that in the quantum statistical approach, we have a different dissolution behavior of the clusters, a different neutron and proton abundances, and a different abundance of the heavy nuclei as the shock wave forms. I know I'm coming to my end. And about hyperons, you can ask me in my break, in the coffee break. I'm happy to answer questions about hyperons as well. And I would thank my collaborators and thank you for your attention.
Thank you, Tobias. Any questions?
Tobias, thank you for drawing our attention to these complexities in the dense matter physics in the neutron star. That's certainly relevant for answering our questions. I have a couple of questions, of course, with concerning the comparison you did with the 87A data. No time, I guess, for the details. So therefore, first a comment and then, or first the questions, and then if time permits, a comment. Do you include in this model the proto-neutron star convection?
No.
Yeah, that's
Not
the
yet.
crucial point here,
Yeah.
because it shortens the emission. And when one wants to do a detailed comparison of the data with the models, it can only be done with convective models, because that shortens, as I said, the emission timescale of the neutrino signal. And also it needs to be done on a statistical basis, because you have to really know how much energy is emitted in late phases and how likely is it to get the corresponding events.
Absolutely. I had no time to do this, Thomas. I did this yesterday in between two sessions, just for fun to see. I mean, I was worried about the results of John as well, but I'm so sorry. Yes, you're absolutely right.
So we are running late, but maybe very short question.
No, please.
No, don't from me.
Sorry. I thought you, yeah. So, what do you think about axions?
Yeah, axions certainly act as additional cooling agent. Any kind of scalar, non-standard model particle extensions would act presumably as a cooling agent that shorten the duration of the neutrino emission in the deleptonization phase. I think Alessandro Mirizzi is worried about convection as well, because that already shortens the cooling time scale, the neutrino emission time scale substantially. Yeah.
More your gut feeling about likelihoods, you know, because that's shown beautifully. It can really alter the neutrino light curves,
right?
And potentially the dynamics itself. So just I mean, as Thomas said, you know, we don't have a crystal ball, but you know.
People have used models without convection intensively. We as well, to constrain unknown, for example, axion-nucleon couplings. If the axions are produced to some CP violating processes, cure, like for example from Bremsstrahlung and from pions as well. So we have been part of this business, but those models, at least our models, did not include convection, and so the constraints derived for the coupling constants, unknown axion-nucleon coupling constants, will most likely have to be revisited if these models were to include convection. In particular, the pions I'm very worried about, because the pions based on the virial equation of state give very large abundances continuously with increasing density in a regime where I think the virial might be questionable to be applicable. Fugacities are very large, certainly on the order of 1.
Maybe we should.
Okay.
So we have the next speaker.